Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video we continue talking about graphs in the context of recursion, and in this video we're actually going to get to write a recursive algorithm. What we're going to talk about is an algorithm to check reachability. So if we go back and we look at our graph that we've been working with, this graph isn't really a very interesting one for reachability. The question is, if I am at a particular vertex, can I get to some other vertex? And it turns out that in this graph, because of the way I constructed it, every vertex can reach every other vertex. However, let's say I were to take one of these out. Okay, I could delete it if I wanted. Actually, let's go ahead. Reattach, oops, that'll work, and then delete. Okay. So what if I take out that? Well, now, if I start at 0, 2, or 3, I can't get to 1. I can get from 1 to any of the others because I have this cycle here that goes around the outer edge, but I can't get to those other ones from 1. So first, let's go ahead and I want to look at how we would write a method to do this. So I'll make this method called canReach, and oops, we're going to pass in the current vertex that we're at as an int. We want to pass in the destination vertex as an int. We need to pass in the graph, and we're going to use the adjacency matrix form. So this will be an array of ints, and this is supposed to return a Boolean, as it tells us either true or false. You can reach it. To make the compiler happy, we can put a value in there. Okay, so how would we write this? Well, I've already given you the hint that we're going to write this in a recursive way. We'll see that we need a little bit more information for this. So what I need to do, if I am at a particular vertex, I need to basically go to all the places that it leads to. And in our matrix form, that means that I pick the row for the vertex I'm at, and I run along, and everything that's not a 0, I try going there. If I ever get to the destination, I'm done. So, well, we should remember when we write recursive methods, we need to make sure we have a base case. There is a base case. So if cur equals dest, simply return true. Else, well, what happens if we aren't at the destination? Then I need to run through all the things in this graph that I can get to from the current location. So I'm going to run through all the weights in graph subcur. Actually, I need to run through indices. For I in graph subcur dot indices, and what needs to happen here? Well, I need to, on each one of these, have a recursive call. So, well, I need to have a recursive call if the value, so if graph subcur sub I is greater than 0, that means that there is a connection between these two. And what I would want to do is then check to see if can reach from I. So I'm following this edge from cur to I. Can reach from I to the same destination on the same graph. I want to call this, but I need to somehow get this together to return something. So I'm going to declare a Boolean. The way I'm writing this right now, it needs to be a var, because I'm going to change it there, and then what I return is red. Now I've done something that might look a little bit unusual to you here. I have this or equal. What does that mean? Well, just like we've seen before, I plus equals 1 is short for I equals I plus 1. The same thing is true here. In fact, you can add any operator you want in front, so that is the same as ret or can reach. So if ret was already true, this will wind up being true. And note that the way this is written, if it's already true, it won't even bother doing the can reach, which will actually help make this more efficient. We can make it even more efficient, though, and we can get rid of the var. So, but this is one way to write this, so that it goes to starts I equals 0, checks to see if we can get from our current location to I, and then if we can, it will try to do a recursive call. Every time that gets ORed on, so as soon as one of them is true, the ret will stay true and we'll wind up returning that. It'll go through all the others, but because this is a short circuit OR, we actually won't call can reach. So this is fairly efficient. An alternate way that we could write this using a higher order method would simply be to say graph sub cur dot indices dot exists I rocket can reach I comma dest comma graph. So the exists method is a higher order method that calls this on each element in turn, which is kind of what we're doing here with the indices. And actually I should say this is a graph sub cur sub I greater than 0, and can reach, because we only wanted to do this if we can reach it. One of the things about exists is because of the way it's written, as soon as one of these is true, it stops. Whereas this for loop will keep going. Once again, because the can reach is on the opposite side of an OR, and it's a short circuit operation, this will run fairly quickly. It'll just be counting up and then skipping. It'll count up, do the if, and then skip everything else. This will actually stop immediately and won't keep going. You can choose either approach that you prefer. So, okay, we have a problem with this, but perhaps it's best to demonstrate that problem by putting in a main. Yes, I did make my graph an object, and we have our thing called graph2. So I can call println can reach. Now, of course, the graph that's still in there is not the one that I changed in the picture. To make it so it's the one I changed in the picture, I would have to do that. Can reach, I want to see if I can get from 0 to 3 on graph 2. Okay, and we're going to run this as a Scala application, and it prints out true, because we can go through there. Now let's try passing it with the 1. And I run, and I have a lot of output here. Notice that can reach is calling, and it's running through over and over and over again we have this line 24 to line 26 to something in range, to line 24 to line 26, repeat, 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 repeat. This is a Stack Overflow. And this just kept calling itself forever and ever and ever. And we could put in a print here to see what's happening with cur, and we'll come back in the next video and we'll actually look at why this is happening and what we're not doing inside of our recursive function. It's something we've actually seen before in a video, just not quite in the context of a general graph. But we'll come back and answer this in the next video.